Good morning, everyone. Welcome back to Historical Geology 1404. Let's get this camera focused on me. There we go. Today, we're starting Module 3. So, hopefully by the time you are in this class, or by the time you are watching this video, you have taken Exam 2. We finished Module 2 last week. We did our review session, such as it was, for Module 2. You had the chance to take the exam over the weekend. If you have not, please take that ASAP. Needs to happen. Okay? We are in the last 2 weeks of this class. I know. It's pretty nuts. We're meeting today. We're meeting on Wednesday. And then Monday. And then Wednesday next week should be our last day. Let me confirm. Isn't that crazy? So let me just confirm those dates here. 20, 22, 27, 29. No, we have finals week as well. We have one more week after that, but that is final/graduation week. So, which is weird to say. Graduation should happen after finals are already done, but here we are. We have 1,800 graduates here at OC this year. So they're having a graduation Monday, one on Tuesday, one on Wednesday, one on Thursday, 3 on Friday, and 2 on Saturday. So, good times. But you know what I just realized? I just realized that my phone is still in my pocket. I just habitually whipped it out to look at the calendar. So I'm going to go plug this into my office so I can set a good example here and not be distracted by my phone. And then we will continue. And I'm back. Let's make sure that camera's focused on me again. Hi, right here. Yep, following me back. Okay. Where were we? Right. So basically 3 weeks left, but the last of that, the last Wednesday, we're going to do what we did last term, which is that's going to be our movie night. Okay, that's going to be our movie day here during class time. Today, I want to send out the Google form so we can actually pick what movie we're going to watch. Let me write that down. My sticky notes seem to have walked off. How bothersome. All right. Movie night. I will send out that Google form. My online students, you also get to vote on that because you also have the option to be here. Unfortunately, it is during normal class time, which means it will be that last Wednesday. The 6th? Should be the 6th, right? Of May. Here in class at 9:30 in the morning. I recognize you cannot be here, or else you would have taken the class in person. That is unfortunate. You can watch the movie on your own and complete the extra credit assignment. I cannot broadcast it to you for copyright reasons, okay? I can watch it through a streaming service that I personally own here, but I cannot stream it to you or else I am in violation of copyright law. So you would have to have access to that movie on your own or be here in person. Normally I would have it on a Friday. Fortunately, we can't do that. Fridays this term for some reason have been a premium for everything going on in my life. I have not been able to have a free Friday. Okay. Any questions before we dive into today's content? Ready to go on my neck, sweetheart? Should we give it a shot? All right, she's content right here. But is she? Maybe, maybe not.
Has she bit you before?
Yeah, once. It's not bad. I don't want her to do it. That's why I have the glove. It's not like a viper bite or anything. So actually, I was my friend Chris, who is a snake breeder here in town. He was up at a reptile show in Abilene, I think it was, yesterday. And there was a guy selling scorpions. And he took a picture of one. And he's like, hey, you were talking to me about wanting a scorpion, right? I was like, yeah, how much is he selling them for? Really reasonable price for an emperor scorpion. But this is a company based out of Houston. So I've been texting them back and forth ever since Saturday, trying to find some way that we can meet up somewhere so that I can buy a scorpion off of them that I can hold here in class for you guys. Especially useful when we talk about things like invertebrates, like trilobites and stuff like that, so I can point out different anatomical structures that we see on something like a scorpion body that are carryovers from a trilobite's body, things like that, right? I've got plenty of vertebrates, reptiles, amphibians. Just don't have any invertebrates in here. Okay. Questions, comments, thoughts, political commentary. Kidding, don't do that. We're on YouTube. Yes?
Okay, so did you see that supposedly Europe is running out of jet fuel?
Europe running out of jet fuel. Interesting. What was the cited reason for that?
The war.
The war?
Those-
Yeah. Yeah, that would make sense. Both wars probably having an effect on that. There are two wars over there right now.
I heard that we got our last, I don't know if this is true, that we got our last like oil or like gas shipment or something.
From Iran?
Yeah, like on the 15th.
So I don't actually know if that is true, if we got a last oil shipment from over there. The Strait of Hormuz is currently contested, right? There are sea mines and ships constantly shooting at each other out there. Afghanistan and Pakistan are still going at it, as far as I'm aware, right? The whole place is a powder keg that is in the process of blowing up. So I can't say for certain what's accurate and what's not. Is it possible that that Europe is going through jet fuel shortages? Absolutely, because you are far more likely to get your fuel from a local source, right? Europe is more likely to get their oil from Iran and Russia and, you know, the Black Sea area and places like that, right? And so since all of the uncertainty over there that's going on, yeah, it's probably likely that it's true. I haven't personally heard about that, but that doesn't mean it's false. Genesis, did you find any more detail about that?
Supposedly it's like 6 weeks left.
6 weeks left in their reserves? Woof, okay. Well, flights to and from Europe might be getting a little pricier. Whoa. Will it last forever? No, because the war won't last forever. Trump and the Ayatollah are just comparing sizes every day, basically, is what's going on. Waiting to see who's going to be the first one to back off. I hate to say it. It's going to have to be Iran. Because, why do I hate to say that? It's not like I support, you know, the Iranian regime, but this war is costing billions of dollars every day. The more we spend on the war, the more in debt we get, and no one is ever going to pay us back for the money put into it, right? So we've invested hundreds of billions of dollars into a war that it's essentially throwing money into a hole for the benefit of a community that will never actually probably even say thank you, right? Whenever Iran comes out of this, and whatever regime or whatever government comes out of this on top, they're probably just going to have to be concentrating on picking up the pieces. Well, there will be no return on the money put into Iran for the American people, which is definitely, it's kind of a sad way to think about it, but it's a way that you kind of have to think about it when you consider that all that money comes from the American people, right? So whatever Trump's intentions were, liberation, I doubt it. I doubt he was wanting to liberate any people. More likely he was trying to liberate oil and keep a nuclear threat contained. But it's an incredibly expensive venture, and they've cut a lot of money from other places to make up for it. And I think it's going to set the American people back a very long time before we make any amount of headway in the places that have been had funding cut as a result of the war. Yeah. What else? Any other thoughts or interesting stories? You ready to move? Come here. Come here. All right. Well, if not, let's get started. Today we're starting Module 3, which is all about the geologic timescale. I already taught you about the geologic timescale, right? Well, starting today, going through the rest of the term, we are specifically going to be discussing the different components of it, okay? Starting with today, we're talking about the eons. Remember, we learned about the eons, the arids, the periods, the epochs, okay? We're starting broad. Why are we starting broad? Why would I just start off today talking about a few eons? We're talking about the first 4 billion years of Earth history today, and then the last 500 million for the rest of the term. Why am I spending one lecture on the first 4 billion years? Huh? They're slow? Are you suggesting that time moved differently back then? Oh, why would we not have as much information? Yeah, I mean, yeah, it started 4 billion years ago, right? But we're going up until 500 million years ago today, right? What happens to prevent there being as much information? There was a substantial part of it that was underwater, but we know that sediment is deposited underwater, right? We have rocks underwater. We get tons of information from underwater rocks out right now. So what else? These are all good thoughts. Just urging you to push a little deeper. What? Okay, so you're referring to something about life, right? The fossil record hasn't been around that long, right? Fossil record is about 3 billion years old, give or take, okay? And so as our fossil record resolves better, being closer to where we are now, we have more of that fossil record for the same reason that I am trying to get you to think about. What'd you say, Ivan? Okay. Huh? There has been more biodiversity. This is true. That's kind of the second point I'm going to get to. I'm still trying to drive home this first point. Okay? Biodiversity increasing, making the fossil record more easy to interpret, absolutely a viable thing. That's number 2. Number 1, though, because we have rocks, we have a few rocks from before there was life on Earth, but not nearly as many as the more recent ones. Why aren't our museums and our private collections filled with 4 billion year old rocks? Why do I only have one in my personal collection? Yeah.
Can I just I would just imagine that after 4 billion years there'd be a lot more ground.
A lot more what?
Ground, or just mass above it.
Over 4 billion years, something happens. What? Weathering is one part of it. Erosion's another component of it. Explosions? What is that? What was that?
Like the asteroid.
The asteroids? That wouldn't really remove such things as ancient rocks. Change their character a little bit, make them a little more interesting. Erosion, weathering, the piling up of sediment and therefore rock. These are all components of what? Remember, there are no dumb answers here.
Deposition.
Deposition's another component of this. Yes, your hand is up.
No, it's not.
Oh, it most definitely is.
No.
What are you thinking right now? What's the answer? My mom is not a viable answer here. Weathering.
You said there was no wrong answers.
I said there were no dumb answers. There's definitely wrong answers. Weathering, erosion, deposition. These all sound familiar, right? These are components of what? I'm going to give you a clue, Emma. It's a cycle. What rocks? Wow, I just gave it away. The rock cycle, okay? What rock cycle have we talked about? The rock cycle, okay? It slipped out of my mouth. Yeah, the rock cycle is constantly going, all these different elements. The Earth is dynamic, right? Earth is dynamic. Things are always changing. Major parts of those changes come from the rock cycle. What's another major driving change factor on our planet? It's the answer to almost everything. It's the answer to why we have a lot of deserts, why we have a lot of glaciers, why weather is the way that it is sometimes, why we have biological distributions. No. Tectonics! There it is! We don't have as much 4.5 billion-year-old rock as we have 100 million-year-old rock because there's been that much more time for those rocks to have been subducted or metamorphosed or any of the other things that come from having active tectonics on our planet. The older the rock is, the rarer it is to find because of how much time has moved forward. Should we try and catch it? Oh, the frog knows it's there. Emma, you might want to move your bag. You want to catch it and give it to the frogs?
I guess I can be the sacrifice.
You're not a sacrifice, it's a cockroach. It's not going to eat you.
I'm too scared. Where'd it go? It's underneath the thing.
It's underneath the thing.
I don't want to squish it. Oh.
It's okay if we squish it a little. Here's a cup.
Oh, here's a cup. Oh, thank you. You got a paper?
I don't have a paper. Let me grab one. Did you get it? Did you get it?
Yeah.
Here. You want to feed it to the frogs?
Sure.
Hold, please, online students. We are feeding an errant cockroach to the froggies.
Oh, my keys are going up. I can hear it. It's okay. Oh, my keys going up.
It's okay. The keys aren't going anywhere. Okay, flip that cup upside down. Let's see, where is he at?
Right there.
All right. Oh! Here, step on it. Or here, it's upside down, right?
Yeah.
Here, I'll get it now. Come here, you.
Bugs. I just don't like cockroaches.
Got it. All right, open up the thing.
Okay. Sacrifice him. Oh, he's gone.
He's right there. He's behind her. Even if it gets out, she'll get it eventually.
That's nice.
All right.
Thanks for making me the sacrifice, John.
Well, I knew that you were capable, and you were right next to it. It was about to go in your bag. Oh, yeah, just put it back on my desk. It has a note on it.
Cup too, or?
Yeah, that's the cup I give them water with. They won't mind if it has some cockroach juice.
Oh, that's nice.
All right, well, that was a fun adventure. Everyone awake? All right, thank you, everyone. Everyone give Emma a round of applause. Yay! Thank you. Okay, so yes, all these things are constantly changing our world, which is why we don't have as many of the old rocks. So let's recap a little bit. What's going on? So we had the Big Bang, which caused all of this hydrogen, aka the most basic element, to appear in the universe. Okay, that hydrogen eventually coalesced together and formed dense clouds. Those clouds created a bunch of gravity because of all those tiny little molecules all in place. Okay, all of that gravity caused essentially all of this mass to collapse in on itself and go what we call supercritical. Okay, and so we get fusion. Fusion of elements together. Okay, hydrogens came together and made what? Helium. Yes, helium. Okay, hydrogens came together and made heliums, and then you get lithiums and berylliums and all of the other things going down our periodic table of elements to a certain point. Okay, this process made everything up through iron, everything else that came later through different processes that are irrelevant to our conversation right now. Okay, but that started about 13.7 billion years ago, near as we can tell. That was our Big Bang period. Then we have these sequences of new stars forming, living for a while, making new elements, and then exploding, spreading all of that matter made through the fusion process through the universe. Okay? All that matter goes on to make new clouds of matter, which then go on to collapse and make their own sort of stars, right? Until eventually you end up with where we are in the universe right now. Our star was formed. As our star formed, heavier elements and lighter elements differentiated from each other in the same sort of way that they did inside of our planet. You remember how the heavy elements went to the middle? Lighter elements went to the outside and are here on the crust? Same sort of differentiation here. The heavier, denser elements made the rocky planets in the middle of our solar system. What are those called? What's this planet closest to the sun? Mercury. Then Venus. Then Earth. Then Mars. Okay, those are our 4 rocky planets, the ones made out of the denser material. Then we have what? Jupiter. Saturn. Neptune. And Uranus. Good. Okay. I don't care how you say it. Uranus, Uranus, it doesn't really matter. Okay? Make whatever jokes you want. Giggle all the want. Giggle as much as you want, people. Okay? Okay. So, yeah, those are the lighter ones, the ones that are made out of a lot of gases. We call them gas giants, in particular Jupiter. Jupiter is the second largest gravitational mass in our solar system. Okay? It wreaks havoc with a whole bunch of other things. So, by the way, did you know that Venus is about the size of Earth?
Yeah, isn't it probably like our sister planet?
You could think of it as our sister planet, where Earth is on the middle, kind of outer half of the habitable zone. Venus is in the furthest in extent of the habitable zone. Okay, do you remember why I'm doing this? It's not the bounds of what we know as habitable anymore. What is traditionally referred to as the habitable or Goldilocks zone is the zone around a star where water can exist between 0 and 100 degrees Celsius, aka between freezing and boiling points. Okay? Because you would presume that all life needs liquid water to survive, as we understand it. Venus is on the innermost extent of that. Okay? It's still technically in the habitable zone, but you know what? It's hotter than Mercury. Mercury, which is even closer to the sun than Venus is.
How does that work? I've always wondered that. Mercury fluid and Venus probably.
Yeah, let's talk about it.
The minerals inside of it?
It's not the minerals, no.
Or is it the atmosphere?
Yeah, it's the atmosphere. She was so excited to raise her hand that she dropped whatever she was holding. That was great. Yes, it is the atmosphere. Venus has an atmosphere filled with greenhouse gases. That means that all the solar radiation that makes its way into that atmosphere gets trapped and stays, which means that the surface got hotter and hotter and hotter and hotter until you have a surface that's, I want to say it's between 700 and 800 degrees Celsius, purely because of the presence of all those greenhouse gases in the atmosphere. Okay? The atmosphere is filled with those gases and a variety of acids that make it very hostile to any sort of probe we try to drop in there. We have sent probes to Venus before. Okay? We've gotten pictures of it. What we're trying to do now, or I wish I could say we, the United States scrapped the missions, they're on the scrap heap, to go and bring back samples of Venus's atmosphere. But you know who hasn't? China. China has several missions going to capture Venetian atmosphere and bring them back here for actual study, which is fantastic. While the United States has slashed our space science budget by a proposed 47%, China has, over the last 10 years, more than doubled their science budget. So the United States seems to be on this trend of we valued the commercial aspect of space travel more, which is why we're going to the moon to build a moon base and start mining the moon, right? Same thing for Mars. While China seems to be doubling down on the we want to understand everything out there. So they are increasing funding in science. So there's this increasing kind of gap, widening gap between us where it may be in the future, if you are really intent on studying space for the scientific value, you may want to go through China. And if you want to study space for the economic value, you may go to the US. I hope that we don't reach that point. I would really love it if both nations were equally invested in both of those. But we'll see. That's the trend that seems to be going on right now. Anyways, so yes, the Venetian atmosphere is the whole reason why it is so hot. You remember what we learned about greenhouse gases? The more of them you have, the more solar heat you retain, okay? It's this positive feedback loop, we call it. Mercury doesn't have an atmosphere. It's just a rock. It's just a ball of rock. No atmosphere. So it literally just, the outer surface absorbs or reflects all of the light, kind of like our moon does. Whereas Venus absorbs all of it. Now, Venus as our sister planet is interesting because it's about our same size, still within the habitable zone, and has a very thick atmosphere. Was there at one point life on Venus? It's a good question. It's a good question, and one that we won't actually be able to know for sure until we can go down to the surface. And maybe, just maybe, see if there's any fossil evidence of it. Now, there are some very fascinating proposals. Based on what we know of the Venetian atmosphere, it is not against possibility that there may be living things in the atmosphere, specifically the upper atmosphere, which is not as hot and has more oxygen than the acid. You got a comment? You were going to mention that? Yes. Aerosol life is essentially what it would be, okay? Suspended in atmosphere, because the atmosphere is so much thicker, so much denser than the atmosphere we're used to here. The right type of life form could remain suspended above that thicker atmosphere, okay? Essentially, think of like, I don't know, airborne sort of amoeba-like things, okay? We already get such things here on Earth, which means that if they exist here, then they can presumably exist in an environment like that, okay? So, very, very fascinating things coming from Venus. There was this thing that happened a while back where people were trying to, it was like far, far, far left anti-fossil fuel groups were saying Earth will become Venus if we don't stop putting greenhouse gases in the atmosphere, which captured attention for sure. But, I mean, the quantity of greenhouse gases you'd have to put out there. There isn't enough oil on Earth to put that many greenhouse gases in the atmosphere. Okay? Just get that straight. What did it to Venus then? If there was not civilization on Venus 50 million years ago that discovered oil and burned themselves to oblivion, then what did it? Most likely scenario? Volcanoes. Volcanoes pump out a ton of gases. Okay? You know what the most common greenhouse gas is? Water vapor. Carbon dioxide is another one. Methane is another one. You can get all of those things through natural geological processes, including expulsion from volcanic vents. Okay? So, it's most likely that there was an extended, extremely intense period of volcanism on Venus, which caused the beginning of this feedback loop that it could not break out of and ended up with Venus where it is now. Could we reverse it? Don't know. Unlikely. Could we ever make Venus habitable? I don't know. Unlikely. Who knows? Interesting stuff. All right. So, yes, that's our planets. Okay, and so now we have our planets orbiting around our star. Now, there used to be a heck of a lot more planets in our solar system. Way more. We don't know for sure how many. We know for certain one crashed into Earth, okay? And we call that one Theia, okay? And that's what made our moon and our current spin at the current angle that we're at and set Earth on this course to make it a viable place for life to begin in the way that we understand it, okay? Maybe even tectonics was started because of this collision. Because Mars doesn't have any tectonics. Why not? Maybe it never got hit by another planet, right? Maybe that's what makes Earth unique. Don't know. Still figuring that out. We'll have to see more planets, get more data before we can confirm that as an actual theory. Mars, no, not Mars, Jupiter sucked a whole bunch of planets into itself, ripped them apart gravitationally. That's where a lot of the moons come from. They are actually captured mini planetoids and giant asteroids. And a bunch of the asteroids that we see around Jupiter and a bunch of the asteroids that we see out in our massive asteroid belt, okay, at the outer edge of our star system, actually have the right chemistry to have been part of planets. What do I mean by that? Well, take a look at this. These are, do you guys know what the difference between a meteorite, an asteroid, and a comet is? Have you heard all three of those terms before? Yeah? A comet is a large celestial object that is on a trajectory, not necessarily in orbit. It needs to have a trajectory, okay? Now, it can be caught in a very large, wide sweeping orbit. We have one called Halley's Comet that will show up about every 75 years or so as it swings around our star system. It's a very, very wide orbit, okay? But it's still kind of, it shifts every now and then, okay? Based on the closest, most powerful gravitational pulls, okay? But it's mostly made out of ice with a little rock in there. Okay, comets are mostly ice, which is why they have the tails. The tails that you see behind comets, that's actually water vapor that's evaporating off their surface because of the solar radiation that's absorbing there and immediately turning to ice crystals. Okay, that's what's making that tail. One thing that a lot of companies are trying to figure out if we can do is harness a comet, bring it into Earth's orbit, and then use the water to alleviate the water issues that we have here on Earth. Very interesting thought. The amount of force required to deviate something that would weigh trillions of tons? Don't know about that. It would take a very long time. You give me 1,000,000 years and a never-ending supply of party poppers, and I will be able to move that comet where we want it to go. But I don't know about the amount of energy required to do it on a faster timeline. That seems like something a little bit beyond what we can accomplish. But we will see. We will see what they scrounge together for that. Okay, so then we have asteroids. Asteroids are either metallic or rocky, with some ice involved as well. There are also very carbon-rich asteroids out there that we can see. Very interesting. Why would there be entire comets made out of carbon? Well, asteroids, made out of carbon. Think about where all of these elements come from, right? The R process, creation inside of a star. When that star explodes, it's going to blast all those particles, all those atoms it made out there. Some atoms like to bond with other atoms with the same atom, right? We know that carbon likes to bond with carbon here on Earth. We find that all the time. It's called graphite. It's called diamond, right? Carbon likes to bond with carbon. And so it makes sense that carbons would combine with other carbons out in space too. And we see whole masses of carbon hanging out there from these ancient supernovae that sent them out into the universe. Okay? So if we wanted to, we could tow one of those carbon-rich things as well. Another fun idea, by the way, organic life requires the presence of carbon, right? What is something required for it to be organic? And I'm not referring to like farm fresh organic. Okay, that just means you didn't use any pesticides or anything to alter it. I'm talking about truly organic. It needs to have that carbon, hydrogen, and oxygen chain that is required for life as we understand it, right? So what if there's a planet that doesn't have enough carbon? What if one day we wanted to, hey, this planet would be great for us to live on, but there isn't enough carbon in its system to have sustainable soil to grow. Okay, throw a carbon-rich asteroid at the sucker. Then wait a million years and it'll probably be fine. Right? Fun idea. Science fiction right now. Let's see. Oh, and then meteorites. So what's the difference between an asteroid and a meteorite? A meteorite is something that is colliding with another object. Okay? So when our astronauts went around the moon last week, they took pictures of meteorite impacts. They were looking at the pitch black side of the moon where both the sun and the Earth were on the other side of the moon, no source of light. The surface of the moon in front of them, pitch black. And they recorded flashes of light, which were impacts of meteorites striking that lunar surface, something we cannot see from our side because it is always in light. Even when the moon is at its darkest, in a new moon, is when Earth is looking at the moon, you can still see it through a telescope. You would not be able to see those flashes unless it was a big old impact. But over there on the far side, no source of light, they saw those impacts. It was great. What's that impact? It's a release of energy. The impact releasing energy, briefly melting the lunar surface before it refreezes again under space conditions. Okay? So meteorites hit Earth all the time. Okay? We even see some in the sky above us every now and then. The easiest place to find them is Antarctica or the Arctic because asteroids or meteorites tend to be darker colored and they show up against the white ice a lot better, right? But yeah, that's the difference between those. Now, meteorites will either be chondrites, which means that they are made out of stone, okay, so rock, or iron meteorites, which is what the Odessa meteorite is made out of, right? I remember I passed around this earlier, okay? This is the Odessa meteorite. I'll put it in front of the camera again for the benefit of my online students, just so we don't forget what that looks like here. Look at that. Pure metal. This is mostly iron and nickel with a few other trace elements in there. There's a little bit of uranium, a little bit of selenium, a little bit of yttrium, a little bit of all that stuff, right? But yeah, mostly iron and nickel, just like the core of our planet. Okay, check this out. This is a meteorite that we found here on Earth. Camera, stay with me now. That we found here on Earth. All of this, that's all metal. You can clearly see that's all metal. What are those little yellow things in there? What do you suppose those are? Any guesses? Huh? It's not gold. It is under a certain type of light to bring out the color a little bit better, but it's not gold. Come on, sweetheart. I'm going to try and put you around my neck now. There we go. There, that's nice and warm, isn't it? Okay. Okay, not gold. Thoughts? What else? It's not pyrite. You would not even be able to tell it's there. That gold color isn't actually the true color of the mineral. It's a crystal of a mineral that you have had some exposure to in my classes. That is olivine. Where do we find olivine? In what layer of Earth? Olivine on Earth is found under the conditions of temperature and pressure in our mantle. This is a section of another planet's mantle that landed here as a meteorite. How old was that planet? Don't know. Was it even a planet that existed in our star system, or did this thing fly for billions of years across the universe to eventually land on our planet? Don't know that either. Very interesting, though. Same composition as our own mantle. Okay, so we learn a lot about the history of our solar system and the universe in general by studying these things, but they can also present a problem, right? Meteorites, every now and then, they'll strike someone's house. They'll destroy someone's car. They'll even land on a person. Very, very, very rarely. Yes?
Like he actually got hit by a meteorite. Like in Monahan?
Yeah?
Yeah, he was young. Like his friends.
He died, right?
No, or like an asteroid. Which was the small one?
Well, meteorites are usually small, but they're also typically traveling through the atmosphere at about 30,000 miles an hour.
I don't know if they hit him there.
Okay.
It was like on the news and everything in one of his.
Got it. Yeah. So, yeah, they hit with enough impact to melt the surface when they hit. So, like, I responded to a meteorite impact out at Schleiermacher Airfield last summer. It had blasted a hole in one of their tarmacs in the asphalt there, which is why they were like, I wonder if that's a meteorite. And I went up there and was like, yep, that was a meteorite. There's a hole, actually a couple holes in the area because they usually break into pieces as they come through the atmosphere. But yeah, very, very hard hitting, okay? So unlikely he was hit by a meteorite. He'd probably be dead. What does happen, though, is every now and then, people will, they'll throw stuff out of airplanes. I'm not even joking, okay? And people immediately think that these are meteorites because, they're 10,000 feet in the atmosphere, right, these planes. And they'll just, they'll just dump stuff because they don't want to have to deal with it. I heard one hilarious case where a guy, his car was hit by something, and they immediately thought that it was a meteorite. And they were looking around, and they couldn't find the meteorite anywhere. But they found a piece of slowly thawing, frozen poop. Somebody had dumped the waste out of their airplane, 10,000 feet up. The poop had frozen on its way down from the upper atmosphere and essentially turned into a flying poop missile that damaged his car.
Isn't it illegal to like
Oh, it
drop
is.
a coin?
It's illegal to drop anything from up there because it picks up enough velocity that it can and will kill people. Yeah. Yeah, it's very, very illegal. So, what's another... Don't go too far down my back, you'll fall again. What's another thing that we can see from these? Well, they can be very dangerous, right? Whether or not your uncle was hit by one, if you were hit by one, that would not be a good thing, okay? So, one comes close enough to Earth, we get worried. There is actually one that's fixing to come pretty close. A couple that are fixing to come pretty close. There is one called Apophis. Okay. Now, when they first found it, they didn't know it had a trajectory with Earth. We have since figured that out. This is the orbit of Apophis. Okay. So here's the sun. This is Earth's elliptical orbit, the blue one. The purple is the Apophis. Okay. Right there in 2029, it's going to pass right next to us. Then in 2036 is when it's going to pass by us again. It doesn't go that far. But you'll see in 2029, here we come around again. Right there. Okay? It's going to pass by Earth. It's actually going to be closer to Earth than Earth is to our moon. You'll be able to see Apophis without a telescope. Now, there is a possibility it may hit. It may hit Earth. If in 2029 it passes close enough that on its way between Earth and our moon, it goes through this 400-kilometer hole. We call it the keyhole. Okay? If it goes through that, Earth's gravity will yank it just a little bit enough closer that in 2036, instead of passing by, it will hit Earth. And they've already projected it would hit the Pacific Ocean somewhere off of Hawaii. Okay? Now, this is a large enough asteroid with enough mass that when it strikes, it would make a tsunami approximately 300 feet tall, which would be enough to wipe Hawaii clean, as well as most of the other Pacific coastlines. We're talking about 500 million people just right there on the coastlines there, and about 250 million people more far enough inland that they would probably still have water. Okay, they would probably still see water. So 750 million people along those coastlines. Yes. So this is something that has been concerning governments and agencies and all sorts of folks that make choices and decisions about this sort of thing for a while, ever since we've known about it. So what has been the answer? How do you deflect something? How do you destroy something? How do you move something that's traveling through space at tens of thousands of miles an hour? Well, the movies like to say, let's blow it up. That won't work. Why can't you blow something like this up? There's no atmosphere. For you to get an explosion, you need atmosphere as fuel. Okay? You need oxygen as fuel. That won't work. Can't just blow it up. So what's the next solution? Redirect it. I like it. Can we nuke it? When you nuke something in space, you don't make an explosion. You don't get a mushroom cloud because there's no atmosphere to light on fire. But you do get a heck of a lot of radiation. Okay? That radiation brings energy. Okay? So when you bombard a surface with radiation, it's going to heat up still, even in space. Now, if enough of your object is water, you can bombard it with radiation, turn that water into steam, and then that steam will propel the object in the opposite direction. You hit a surface covered in ice, it turns to steam, steam goes that way, object goes that way, right? Einstein's laws of motion, right? So that's one idea. What if there's no water on your object? You'll just heat up your rock or heat up your metal, and it'll just continue on its merry way for the most part. What do you need? Our only answer here is to redirect it with kinetic force. Okay? You use kinetic force. You throw a bullet at it, basically. The bullet isn't meant to go through it. The bullet is meant to hit it with enough force that it pushes it slightly off course. Okay? So while our asteroid is going around its orbit, we are projecting where it's going to be and then calculating the exact right time and velocity that you need to launch something at to hit it at just the right angle so that its orbit shifts just a little bit. Even if you only shift its orbit 0.1 degrees, then by the time 2036 rolls around, it could be 100,000 miles away instead of right next to our atmosphere, right? So that's what people are working with. And we have tested this technology on smaller bits of rock out in space, and it does seem to work. It's called DART. Okay, this is what they do. The project is called DART. So this is our answer if there's ever a threat like this. All right, any questions so far? All right. So let's talk about the Precambrian. We've discussed how our solar system was formed. We've discussed the beginnings of our planet. Now, from the furthest back that we go on our planet, all the way up until 4 billion years. So 4.54 billion years, all the way up to 4 billion years, we call it the Hadean. That's basically Earth was molten, mostly liquid. Towards the end of the Hadean, we start seeing the formation of an outer crust. Okay? Then we have the Archean, which goes 4 billion to 2.5 billion years ago. Then after that is the Proterozoic, which goes 2.5 to 541 billion years ago. Okay, so we have a half billion period of time, a 1.5 billion year of time, and a 2 billion year of time that we're talking about today. The Hadean, Archean, and Proterozoic. Starting with the Hadean, Earth is collecting mass through all of the comets and asteroids and meteorites and other small planetoids that collide with us. Okay, every time we experience a large collision, it re-melts this mass of rock. Eventually, it's going to stop getting hit by enough stuff that it starts to cool off, but not quite yet. This is when we start to see the Earth spin. This is where the moon comes from during this time. Let's follow this link here. Hopefully it'll work. Here. Okay, check this out. This is Earth being collided with the other planet. What? Hold on. Why can't you see that? Yes, no, that music. That's all you needed. Yeah. Hold on. Let me... Oh, I think I know why. because this is still widescreen, let's close the widescreen. Can you see it now? No. Yes, can you see that?
Yes.
Great. Okay, now let's play it. Okay, so there's Earth and then the Theia. Okay, that big blob, that is not the moon. That's going to recollide with Earth. See that smaller blob out there? That's part of the moon. Okay, so that big blob hits Earth again, remelts it. Okay, watch this with a different. Okay, you got that string of debris, two blobs hanging out in space. That big blob is going to recombine back with Earth, and that's going to become our moon. Boom, rehit, remelting. We had our own asteroid belt for a little bit. Bunch of debris strung out around us until it all recombined back with Earth. Look, there's actually a second moon we had for a little bit. Before it got ripped apart into that belt of debris that ended up hitting us again. Okay, so that's how our moon formed. Isn't that interesting? Okay, it took me all the way back to the beginning of the slideshow. Hold on. All right, this is how Earth got its spin. This is possibly how Earth also got its tectonic activity through the same process. All right, now towards the end of the Hadean, come on now. Hello. There, oh, no, it went too far. All right, towards the end of the Hadean, the ocean started to form. Where did the oceans come from? Where did we get all that water? Yeah, exactly. Impacts. Every time we got an impact, that thing that hit us brought a little more water with it. Okay? Where else do we see a lot of water forming from? What were we talking about earlier where a lot of the byproduct is water vapor? Comet and asteroids, they bring it with them, but water vapor is also the result of... We're not talking photosynthesis yet. We're not there yet. This is the Hadean, no life. Volcanoes. Yeah, you remember we were talking about that? Water vapor is the main gas that comes out of volcanoes. Okay, so a combination of comets bringing water here and then chemical reactions inside of magma causing the formation of water gas, okay, coming out of a volcano. Those two things put a lot of water in the atmosphere. You get a lot of water in your atmosphere. Eventually that water is going to fall in the form of rain. It starts to collect on the surface. Okay, so we are seeing the development of early atmosphere and the development of early oceans. Now, this atmosphere is not something that you would want to breathe. It's melt your lungs kind of stuff, okay? A lot of ammonia, hydrochloric acid in that atmosphere, okay? And by the way, the surface is still extremely hot. The crust, such as it is, very thin. Lots and lots of heat at the surface, okay? Okay, during the Hadean is when we start to see Earth layers start to separate from each other. The outer crust made out of mostly those lighter elements, and then the mantle. The core started to form as well with the denser elements that are slowly making their way towards the middle of our planet. Okay? Our early crust, we believe, was very rich in feldspar. Why? Well, because when you conduct some lab experiments with what we believe early Earth was a mix of all the different elements and minerals that started to form early on. According to Bowen's reaction series, well, you start forming things like olivines and pyroxenes and stuff in your hotter, higher pressure areas. You start to form your plagioclases and your other feldspars out on the outer surface. Okay. Early continents start to form as well. What causes this? Presumably volcanic activity. Where you get volcanoes, you get a buildup, a thicker layer of rock on the surface. These proto-continents, we call them, are simply zones of slightly thicker rock than the rest of the crust around them. Now, during this time, we see a little bit of tectonic activity maybe happening. Okay? Convection started to occur, and where convection occurred, you get that spreading apart and colliding together of your plates. Okay? So those proto-continents, just slightly thicker zones, would collide with each other and make microcontinents. So we're going from proto-continents to microcontinents. Excuse me. Man. All right. Now, as our Earth continues to cool and these collisions continue to happen, the rate at which our continental crust differentiates itself from the ocean crust increases as well. Oceans get deeper, continents get taller. Okay? Now remember from that video I showed you earlier on in the semester where it was that model of the different continents forming, the first ones were very small, basically large islands. Then they collided with each other and made even bigger sections, right? Until eventually those islands would collide with each other and make what we would call continents today, right? During this time, we see things called greenstone belts. Greenstone belts happen because there was not enough oxygen in the atmosphere or free oxygen in the water to cause things to rust. Okay? So where today, leave something out, something metallic out long enough, it will rust. That's only because of the presence of oxygen. There wasn't enough free oxygen for this to happen way back then. So we get, instead of red rocks, we'll get green rocks, rich in minerals like chlorite that would form under those conditions where you would not get, where would you not have oxygen. Okay, so greenstone represents some of the oldest rocks on Earth. I have a piece of greenstone from the greenstone belt in Canada in my collection. It's about 3.5 billion years old. There's a very large greenstone belt in South Africa as well. Pretty cool. I'd love to go there and get a sample from that one at some point. Okay, so we have moved on into the Archean. Okay, we've left the Hadean behind. We are in the Archean. Okay, so between 4 billion and 2.5 billion years is where we're at now. Okay, is when all this is happening. Now, why do we call this the Archean? Why do we separate it from the Hadean? Do you remember when we learned about the different types of life? Huh? Yeah. The two earliest forms of life that we have record of are bacteria and archaea. Now, how do we know that there was life during this time? It's not until further into the Archean that we actually have fossils. So why do we draw the line for the beginning of life where we do now at 4 billion years? No fossils. That doesn't mean there's no evidence.
At the very bottom, the organisms become that live in the
So those are the ones that we believe existed at that point in time. But again, there's no fossils for them. Not that far back, not 4 billion years. It's not so much a trace fossil as much as it is an environmental result of life. Okay? This is called a banded iron formation, and I have one right here to show you. Okay? We call these BIFs, banded iron formations. Let me take the dust off of that. Look at that. Can you see that pretty well? If I flip it over that way, maybe. This side's a little more vibrant but darker. This one's a little less vibrant but lighter. See that? What do you see? Describe. You see lines. Describe the lines. Yeah, there's some thick ones and some thin ones. That definitely has good information. But what else can you tell me about it? There's red ones. What makes things turn red? Oxygen doing its thing. Oxidizing iron specifically. So what we have here are layers of sediment that are not oxidized, and then layers that are, and layers that aren't, and layers that are, and layers that aren't, and layers that are. We look at this, and what do we think? There's periods of time where there's more oxygen and periods of time when there's not. There is no geological reason for why oxygen would all of a sudden be showing up. So what must be doing it? Photosynthesis. What does photosynthesis do? It cracks the oxygen off of gases and spits the oxygen back out. That's its byproduct, right? That's why we like trees. Trees make oxygen, we breathe oxygen. Huzzah! This is the earliest evidence of life on our planet, and it is 4 billion years old. Okay? That's why banded iron formations are super cool. So, what does it mean that it's happening in layers, though? Oxygen, no oxygen. Oxygen, no oxygen. Why would all of a sudden we go from there's more oxygen to, oh, there's none? Or very little? There are no plants. We're just working with archaea and bacteria right now.
It has something to do with our natural like cycle. Do you show this of like the Earth's hot and cold period?
It's very similar to that. What happens when you increase the amount of oxygen in the atmosphere? Right, we decrease the amount of greenhouse gases, increase the amount of oxygen, drop the temperature. Drop the temperature, things that like the hot die. So what we're seeing there by, oh, my camera's not looking at me anymore. Hi, right here. What we're seeing in these banded iron formations, why is it looking up there? Hello? Hold on. What we're seeing in these banded iron formations is evidence of life is slowly starting to do its thing and then collapsing, dying because of temperature change, and then slowly doing its thing and then dying because of temperature change. Hello? Yeah. Oh, why are you zoomed in so far? Jeez. Zoom out. There we go. Okay, so it's doing its thing and dying, doing its thing and dying, and doing its thing and dying. Okay? Until finally it adapts to the point where it can survive in the new conditions caused by the fact that it is putting all this oxygen out, okay? It's not spitting out oxygen intentionally. It's the byproduct of its chemical reactions inside of itself, right? It has to suffer the consequences. Now, there are only prokaryotes during this time that we have evidence of, okay? There might be some evidence that we saw some eukaryotes towards the end of the Archean, middle-ish to end, but right now in the early Archean, just the early prokaryote stuff. Okay? Let's see. Okay. Now, where did this life start? Those ocean ridges. The chemosynthetic bacteria and archaea that we still see living at the bottom of the ocean at these mid-ocean ridges. Okay? This is where life actually began, we believe. Okay? Chemosynthesis is a heck of a lot closer to what bacteria and archaea naturally do than photosynthesis is. So chemosynthesis must have come first. Okay, makes a lot more scientific sense. And then photosynthesis was the result of these organisms trying to go from the bottom of the ocean up closer to the surface. Okay, so why did they survive here in these conditions at the bottom of the ocean? Well, there was plentiful chemicals, right? The metals that get spat out from these mid-ocean ridges gave a lot of chemicals for these chemosynthetic organisms to split parts off of to sustain themselves. What is consumption at all except the stripping away of materials that are needed, the removal of the excess waste you don't need, right? When you eat a sandwich, you are stripping everything, your body is stripping everything it needs to sustain itself out of that sandwich, and you poop out the rest. That's literally all that happens with chemosynthesis as well. Except instead of needing sunlight to do it like a plant, you just ingest it, strip it apart, and spit it out. Just very similar to what we do. Okay? Towards the middle-ish to end half of the Archean is when we start seeing the first evidence of actual stromatolite-looking creatures, okay, or organisms, colonies of these creatures, okay? So remember what a stromatolite is it's a buildup of these celled organisms, algae, except we don't actually have algae yet. These are pre-algae, okay, which are building up layer upon layer upon layer upon layer upon layer upon layer as sediment is then shoved on top of them. So sediment, layer of life, sediment, life, sediment, life, sediment, life, building that sort of mushroom shape, okay? This is an ancient stromatolite colony that you can see here. You can think of these as the first reefs, okay? What is a reef? It's a whole bunch of life that's built up into this gigantic mound shape, okay? Usually in an attempt to remain close to the surface of the water for sunlight, access to sunlight for photosynthesis, okay? Bless you. Okay, so that's your Archean. In the Proterozoic, which was 2.5 billion to 541 million years ago, we have a lot more fossil and geological evidence for what happened during the Proterozoic than we do for the previous 2 eons. Okay, there's just a lot more preservation. We have larger continental masses to preserve that evidence on. Remember, we were working with microcontinents and protocontinents for those first 2. So just tiny little sections of stuff that got slammed into each other, slowly accreting on top of each other. Starting in the Proterozoic, we have larger continents, way easier to make interpretations where the data has been saved, right, in the rock record. So from this point, I'm going to be telling you about these things called orogenies, okay? An orogeny is a mountain building event, and this is going to be very relevant to a future exam that you take. So you really want to take good notes on these orogenies, okay? There's also going to be something else called cratonic sequences that I'm going to be showing you later on. You'll want to take note of those as well, okay? I'm only telling you about the major mountain building events that are relevant to North America. Not telling you about the ones for the entire world across every continent, because that would take forever. Just the ones relevant to you and me here in North America, okay? So the first one is the Watmeh orogeny, which was 2 billion years ago. What happened here was our province up here, which this right here, this kind of circular area, that's all that's left of it, preserved in northern Canada, okay? But this was its own microcontinent before. This is what's left of the microcontinent. We call it the Slave Province, okay? I didn't name it. Someone else did. Now, over here on the west edge of that is called the Watmeh origin. That is where another continent slammed into the Slave Province here and made a giant mountain range. This is the first major mountain range, mountain building event that would go on to later make the North American continent, okay? Now, in the Proterozoic, our environment became very cold. Why would that happen? The oxygen is doing what? It's making it too cold because it's replacing the greenhouse gases in the atmosphere. As those greenhouse gases are getting sucked in by something. What's causing it to become cold? Besides the oxygen is coming from what? No.
You pointed at me like I was
What is spitting out oxygen as it's consuming the greenhouse gases? Not plants. We're not at plants yet, but it is life. Yeah, the bacteria and the archaea and all the living stuff that's happening, right? During the Proterozoic, we see very cold temperatures. Why? Because life exists. Between chemosynthesis and early photosynthesis, yeah, we're starting to see actual effect on the Earth's entire climate as a result of this life, okay? There's glaciers on those ancient cratons, which are those microcontinents that now form the core of our current continents, okay? We see the development of cyanobacteria. Think of it as the next iteration, okay, of bacteria, making larger colonies, okay? Eukaryotes definitely are around during this time. They may have been around before, but they absolutely are around now. Eukaryote, essentially, several prokaryotic cells that evolved, adapted to work together towards a common function, a common goal, okay? So as we start to see the development of eukaryotes, we see things like algae show up. What is this? This is a coil algae right here. This is essentially a string of cells all working together in a colony. Early algae. Okay.
Isn't that how they say like eukaryote cells formed by prokaryotic cells working together and then soon combining it?
Yes, it's called endosymbiosis. Okay, endosymbiosis, where two cells, one cell was consumed by another cell, but instead of ripping it apart for what it was made out of, for some reason, due to a mutation, it didn't. And so the other cell, the producer cell that was consumed, began to share its energy with the larger cell. It got protection. Okay, it's a symbiotic relationship. Do you know what symbiosis is?
What is it, like the alligators
And those birds? Yeah. The birds come and pick the meat out of the alligator's teeth. Well, the alligators leave their mouths open, right? The alligators don't eat the birds because the birds are picking the pieces of meat from the teeth so that they don't get tooth rot. Right? Yeah. Okay, that's an example of symbiosis. That's what's happening here. Both parties benefit. Now, there were several giant irradiations that happened here. Remember, a radiation is when life diversifies or expands to fill new evolutionary or new biological niches, okay? So, 750 million years ago, we see the first things that look like amoebas. This is what they look like, okay? This is the actual fossil of one, and then this is a rendering, kind of an artistic illustration of that, so you can kind of tell them different. Each one of those is a different cell. Okay, there are cells along all these walls. There are cells here along the inside. The different colors represent the different functions that they perform. Some are digestive cells. Okay, some of them are protective cells. Okay, some of them are information. Some of them are genetic cells. They all are working together in this earliest, what you might call, animal. Okay, amoebas are basically animals in function. Okay. Excuse me. 650 million years ago, we start to see early sponges. This is what they looked like. These were animals, so multicelled organisms now, okay, just like the amoeba, that grow. They have specialized cells for making these shells around themselves, okay? They grow these exoskeletons. Now, eventually, sponges get bigger, they make colonies. Okay, so all of that happens in the future. But these are the earliest sponges. Then, 570 million years ago, we see the development of what we call the Ediacaran fauna, or Ediacaran, depending on which continent you're from. Okay, these come from Australia. These no longer look like algae. They no longer look like amoebas. They look like, well, I mean, this kind of looks like a leaf. These kind of look like sand dollars. That looks like a worm, right? They look like all sorts of things that we might have in the oceans now. How fascinating. Here's the mystery. How did we jump from algae and amoebas and tiny little sponges to that? There's like nothing in the fossil record in between. That was a massive jump, which is why the Ediacaran fauna is very, very, very interesting. Now, why else is it interesting? We found the Ediacaran fauna in extremely fine-grained, perfect preservation sediment. Okay? Who knows what other things could have been alive that we do not know about simply because they were not preserved in the right environment? You okay over there? All right, pay attention. Okay, so that's the Ediacaran fauna. There are even some skeletal things that we have found in that fauna, in those fossils, that we can't explain evolutionarily yet. Okay? Some really complex life was developing, obviously, before then, because this didn't just pop out of nowhere. Okay? We just don't have the fossil evidence for it yet. This is one of the main reasons why there's this big push to shove the end of the Precambrian and the beginning of the Cambrian back in time, because this is 570 million years old, and right now the Cambrian begins, which the Cambrian is when the first complex life explosion began, is at 541 million years ago. Okay, so this is a big reason why we want to push that back. It only makes sense. We have evidence that it began sooner than 541, but again, like I mentioned last time, it takes forever for the scientific community to agree like that on anything. Okay. As the oxygen increased and temperatures decreased, there was a massive environmental effect. We call this snowball Earth. Between 750 and 650 million years ago, Earth would have looked like that from space. Covered in ice. Remember, our continents aren't that big anymore. We have glaciers. The continents are covered, or they're not that big yet, I should say. The continents are covered in glaciers. And those glaciers have kind of spread out from there, covering a lot of the oceans. Only in strips around the equator and a few other isolated areas would you have liquid water at the surface. So, we saw an extinction. As a result of that extinction, only the organisms that proved themselves capable of rapid adaptation survived. That set the stage for the necessary rapid adaptation that would come later. Okay. We start seeing the development of all these different mountain ranges. Microcontinents are accreting on top of each other. I've already talked about that. One slams into another. You add the mass together, you get another larger continent. Okay. All of those Archean continents that we saw, the microcontinents, they came together and they made the supercontinent, the first supercontinent, Laurentia. Laurentia existed from 1.95 to 1.95 to 1.85 billion years ago. Laurentia is what we call now are the separate sections of North America and Greenland. Okay, they will come together and make Laurentia again in the future, but this is the first one. Okay, that's relevant here anyway. Okay, so we get Laurentia, North America plus Greenland. After that, from 1.8 to 1.4 billion years ago, Laurentia gets incorporated into all these other microcontinents that come together and make Nuna. Okay, so here's Laurentia right there. Now this section right here, that's part that's kind of stripy right there, that's called the Grenville orogeny. I'm going to talk about that in just a second here, okay? But here we have elements of all of the other future continents showing up. There's Antarctica, Australia, India, West Africa, Siberia, Baltica, South America. This is North China. All this yellow stuff binding them together, that is continental mass that no longer exists, okay? Following the breakup of Nuna, from 900 to 630 million years ago, we get Rodinia, okay? So Rodinia included Australia, China, Antarctica, and Laurentia. Then that broke apart. Some people left the party and some people joined the party. This is kind of what happens with supercontinents. It's like watching a band, okay? The band will break up, and then a year or two later they'll come back together, except one guy will not come back, and so they'll have to replace the drummer, right? And then they'll break up again a few years later, and then the guitarist and the lead singer won't want to come back, so they'll have to replace those guys, right? Okay, so in Pannotia, from 625 to 550, we have Laurentia, Africa, Baltica, South America. So it's just we keep swapping things in and out. All right.
Did the drummer and singer go and find a different band?
Yeah, sometimes we'll have several other continents going at the same time. Like right here, this is when we have Africa, Pannotia, Laurentia, Baltica right here. Antarctica and Australia are hanging out together. India's off doing its own thing. Siberia's off here doing its own thing. They're in their solo musician arcs, right? Then we have Gondwanaland, which started 550 million years ago and continued into the Cambrian. So we'll pick up with Cambrian with that later on. in our next lecture. That included Africa, India, Australia, and South America. So Laurentia's off doing its own thing now. It's been part of the party the whole time, and now it wants to go and do its own thing. So yeah, they keep swapping in and out with each other. But every time that they swap in, their mass grows a little bit bigger because they are picking up more mass from the simple act of colliding with each other. Okay, so as time goes on, you're going to notice that our continental mass continues to increase over time. Like, look how big Africa is here versus how big it was here, right? All right, so now we have that Grenville orogeny, which I mentioned, which I pointed out, I should say, right here on the southern edge of Laurentia. That's the future Grenville orogeny. Well, now we're going to talk about that Grenville orogeny, okay? This was what happened when Laurentia and a bunch of microcontinents slammed into each other. This is what made Laurentia almost double in size during this time period. Okay, whole bunch of other stuff slammed into that southern coast, increasing to the mass of what would become our North American continent. Okay, 1.85 billion years ago, there was a massive asteroid impact. We call it the Sudbury impact. It hit right here in Ontario, what we call Ontario now, okay? And this impact was so huge, it picked up chunks of modern-day Canada, what would we call Canada today, and threw them 800 kilometers away. Literally ripped up pieces of Earth's crust and chucked them 800 kilometers away across the Earth. It ripped a hole in Earth's crust large enough that the mantle rose up to the surface. And then cooled off real quick. Okay, it cooled off pretty quick. But this represents a really cool zone where the mantle is still significantly closer to the crust than it is almost anywhere else on Earth. Sure, it's got 1.85 billion years of sediment built up on top of it, but it's still closer than it is around the rest of the planet for the most part. And since we get a lot of very valuable metals out of the mantle, this is where a lot of mining companies have built up. So right here, in the actual impact crater itself, there are several, I want to say like half a dozen major, mining companies that are actively mining inside of that crater because of how close the mantle is to the surface. But can you imagine seeing that thing? This is bigger than the impact that killed the dinosaurs, by the way. Oh, it definitely caused an extinction. But remember, 1.85 billion years ago, the only things we had were those bacteria and archaea. Right? So they didn't even notice, probably. Right? A bunch of them died, but it didn't make a difference. Enough stuck around. Okay. Any questions? Because that's all I got today. Yeah, that's it. You can start working on Lab 4. Lab 4 is exactly the same as Lab 3 if you haven't started working on that yet. Exact same format, even a lot of the same material. Okay? Same concepts. I don't really need to go through it because it's literally a continuation of the same sort of project. Any questions about anything today? Okay. Well, then I will end the recording here.